Okay, maybe this is a good time to start. Welcome, everyone. My name is Yasemin Didem Aktaş. I am a UCL Associate Professor, and I am also the co-chair of UNESCO Chair in Disaster Risk Reduction and Resilience Engineering. I am very happy to open the webinar season this year with a talk by Isabelle Tingzon on harnessing AI and Earth observation data for climate resilience and universal school connectivity. So it is a talk that is very much in line with our scope thus far. It is going to be composed of two separate talks with specific emphasis on the Caribbean and small island developing states. But before that, I would like to walk you through some developments that have been happening within our UNESCO chair. First of all, we are very, very happy to announce that we extended our UNESCO chair for another 4 years. So we are going to be doing this for another 4 years along with our research work. For this year, for our webinar season, we have identified 6 thematic lines. These are from imagery to analysis for disaster risk reduction. The second one is the application of AI to support infrastructural resilience, and Isabelle's talk comes under this theme. Economic loss assessment and prevention, holistic system resilience. This can include education policy, research and training. We are doing structural resilience and also public health considerations in DRR. We started to schedule our talks. You can see the details of these on our website as always. We are starting today with Isabelle's talk. Then in October, we have another one that focuses again on AI and resilience. And in November, we have a talk by Virginia Murray and John Rees that is going to focus on hazard information profiles. I also would like to take this opportunity to tell you about a separate research webinar, which happens to take place on the same day as our second chair webinar on the 16th of October by our chair researcher, Ahsana, and other long-lasting colleagues on the accessible and affordable decision support tools for infrastructure resilience. For further details on this research webinar and details as to how to register, you can again go to our website. So coming back to our talk today, I would like to say a few things about Isabelle. Isabelle is a junior professional associate and a geospatial data scientist at World Bank. She has been doing a lot of work on especially AI-driven climate resilience projects in the Caribbean, where she's going to highlight a number of different sort of work streams under her lead. And she also has been previously a data science consultant at UNICEF, where she led the research development and deployment of UNICEF's Giga AI-enabled school mapping work, which is again going to be featured in her talk today. But before further ado, I would like to invite Isabelle to share her screen and start with the talk. Thank you very much.
Thank you so much, Yasmin. So let me share my screen. All right, so good morning, afternoon, and evening, everyone. And thank you as well. Thank you again to Yasmin, Raphael, and team for the invitation to present and for the generous introduction. Again, I'm Isabelle Tingzon. I'm a JPA at the World Bank and previously a consultant at UNICEF. It's a pleasure to be here virtually to present to you about our work on bridging data gaps in the Global South, harnessing AI and Earth observation for climate resilience and universal school connectivity. So as mentioned earlier, I'll be presenting 2 projects that I've had the privilege to work on related to generating AI-derived infrastructure datasets for humanitarian operations. So the first will be on mapping housing stock characteristics for resilient housing and infrastructure in the Caribbean. So this was work done under the Digital Earth Partnerships team at the World Bank under the Global Facility for Disaster Reduction and Recovery, or GFDRR. And again, the second presentation, the second half of the slides will be describing my work at UNICEF on large-scale school mapping using AI and satellite images to advance universal school connectivity under what is called the GIGA initiative. So going now to the first case study, Just a bit of context. As you might know, the Caribbean is among the most climate vulnerable regions in the world due to the prevalence and intensity of extreme climatic hazards. These hazards include, for example, floods, landslides, hurricanes, and in recent years, Category 5 hurricanes have devastated many small island developing states, with the highest degree of damage and losses often sustained in the housing sector. So for example, in 2017, Hurricane Maria damaged roughly 90% of Dominica's housing stock, accumulating costs upwards of 380 million US dollars in the housing sector alone. And so these disasters have spurred ambitious climate resilience initiatives by national government agencies. And for these climate resilience initiatives to be successful, governments typically require complete and accurate and up-to-date information on housing stock. Unfortunately, housing stock data tends to be limited, incomplete, inaccessible, or even completely non-existent, especially in many developing countries and small island developing states. So in response to these challenges, my team and I returned to AI and Earth observation to help fill in these critical exposure data gaps. So under the Digital Earth Partnerships team, our goal essentially is to enhance local capacity to leverage AI and Earth observation for resilient housing operations. So the Digital Earth Project has three main components. So the first is capacity building. This involves establishing, for example, GIS units within governments and training government staff in using, maintaining, and collecting geospatial data sets, and also using tools and services related to this. The second pillar is operational support. This is support in terms of generating, integrating, and using critical baseline exposure data sets and using AI and Earth observation technologies. And the third is, of course, knowledge sharing and dissemination to encourage wider adoption of these methods and tools and data sets across the Caribbean region. So in this presentation, I'll be focusing mainly on the second pillar, which is operational support in terms of AI and Earth observation technologies. So in this project, we used a number of Earth observation data sets, namely one very high resolution aerial images, mainly in the form of drone images and aerial orthophotos, which I'll talk a little bit more about later. We also used LiDAR-derived data products in the form of digital surface models, digital terrain models. We also used building footprints that were delineated from the aerial images. And lastly, we are currently exploring the use of street view photos taken using GoPro cameras mounted on top of cars. So in terms of the very high resolution aerial images, we used mainly two types. So one is nationwide aerial orthophotos. So these were taken by attaching a camera to an aircraft and flying it all across the country. So in this case, we have Dominica and St. Lucia. And this resulted in 10 to 20 centimeter per pixel resolution aerial images. And while this gives us complete coverage, it's also unfortunately very costly and therefore unsustainable to acquire on a more frequent basis. And so in response to that challenge, we look towards drone technologies to generate higher resolution images, ranging from 2 to 5 centimeters per pixel. It's definitely less scalable compared to using aerial orthophotos or satellite images, meaning it's unlikely that we'll be able to get nationwide coverage and more likely that we'll only be able to get images in local regions. But it does have the advantage of being cheaper, allowing for more frequent data acquisition, which is, of course, critical in disaster contexts. And part of the project actually involves training government staff to operate drones to enable them to collect these very high resolution aerial images on a more frequent basis. And next, we also used LiDAR-derived data products. Here, these are taken from 2018 to 2022 at a resolution of 50 centimeter per pixel, again, across Dominica and St. Lucia. And the way that we use these LiDAR data products So here we show you how we generated the normalized digital surface model, or NDSM, which was derived using what is called the digital surface model, or DSM. And this essentially just represents the topography of the Earth's surface. This includes man-made and natural features, meaning buildings and trees. And the DTM, or the digital terrain model, represents the bare Earth model and is absent of man-made and natural features. And getting the difference between the DSM and the DTM allows you to generate the height of features and above the ground surface, which we call the NDSM. All right, so now for the AI component of the work. So we start by leveraging what is called the segment anything model, or SAM, to extract building footprints from very high resolution aerial images and aerial orthophotos. So we quickly note here that we used SAM for building delineation due to misalignment issues that we saw with locally acquired drone and aerial orthophotos and existing building footprint datasets from, as you can see here, Microsoft Building Footprints, Google Open Buildings, and OpenStreetMap buildings. So the segment anything model allows us to generate building footprints that are more aligned with our underlying aerial images. And then given these aerial images and corresponding building footprints, or derived building footprints, we then manually labeled around 15,000 buildings based on two categories. So we have roof type, or roof shape, and roof material. And I'll discuss this in a little bit more detail later. And for this work, we trained simple convolutional neural networks, or CNNs, to classify the images of the buildings based on the different roof categories using each data source. So optical, RGB, aerial images, and then LiDAR data. So we did this first separately and then combined. And then furthermore, we also experimented with different data fusion techniques for combining RGB images and LiDAR data. So here we demonstrate feature level data fusion, where basically from each CNN model, we extract dense feature embeddings using each data source. And then we concatenate it and use this concatenated input into a downstream ML classifier, as you can see here. And then we also experimented with two different approaches for decision level data fusion. So one is basically computing what is the mean of the softmax vectors, which are basically the output probabilities of the model. And the second being concatenating these softmax vectors and using this as input again into a downstream machine learning, like simple machine learning classifier. And what our work indicates is that for roof type classification, the LiDAR only model performs marginally better than the RGB only model. But for roof material classification, the RGB only model performs considerably better than the LiDAR only model. And furthermore, our work also indicates that feature level data fusion consistently outperforms decision level data integration for both classification tasks. And we also show that models trained using a fusion of RGB and LiDAR data consistently outperform models trained using any one data source alone, with our best models achieving 93% F1 score for roof type classification and 92% F1 score for roof material classification on our test set. So just to summarize our workflow, again, we start by taking our aerial images of the building, running it through the segment anything model to generate the building footprints. And then for each building footprint, we then crop the image using a minimum bounding box and run this through the trained computer vision or convolutional neural network model to generate the roof attributes. And you can see here using our models, we were able to classify our images based on, again, roof type. So roof type being flat, gable, meaning it's pitched on two sides on the central ridge, hip, meaning it's pitched on three or more sides, and no roof, meaning the roof is non-existent. We also classify buildings based on roof material. So we have here concrete or cement, healthy metal. We also have irregular metal, which basically is metal with some form of rusting, patching, or damage. Blue tarpaulins, which is typically prevalent in post-disaster contexts and is indicative of major damage. And finally, incomplete, meaning it's either, again, under construction or severely damaged. Right, so we show here how we were able to generate nationwide roof type and roof material classification maps with accuracies of 92 to 93% across St. Lucia and Dominica. And then right now we're also in the process of evaluating how well the model generalizes to new countries like Grenada and St. Vincent and the Grenadines. All right, so here we show that through a regular collection of very high resolution aerial images, can use these tools to efficiently identify high-risk structures and also rapidly assess building damage after a disaster event. So for example, we show pre and post-disaster roof material classification maps in Dominica. So you'll find that a lot of the buildings initially were classified as healthy or irregular metal, as you can see in green and red before the disaster, which then changed into incomplete or blue tarpaulin in purple and blue, respectively, in the aftermath of Hurricane Maria. And finally, one of our ongoing works here includes using street view photos to capture building characteristics, such as building material, building completeness, number of stories. So this involves collaborating with local communities to collect street view photos using GoPro cameras that are mounted on top of cars. And similarly, we are employing computer vision models to detect buildings and extract attributes from these street view photos, as you can see here. And the last step for this work is attributing the building characteristics derived from the street view photos back to the corresponding building footprint, thus enriching our exposure data layers, where we now have attributes that are derived from both aerial images and ground level photos. So yeah, here we essentially just emphasize the need for a bottom-up approach that involves local communities in the collection and generation of critical housing stock information. This is to ensure, of course, sustained adoption of these technologies. And through this, we hope to essentially employ solutions that ensure ecosystem integration, solutions that fit local needs and build long-term capacities. So again, to develop sustainable AI solutions for disaster risk reduction, we do emphasize the need for responsible and inclusive approaches that enable co-creation of geospatial data sets that build local capacity, and develop local skills, and rest on strong ethical frameworks to protect the most vulnerable populations. So that ends my first presentation. I will be moving on to the second presentation now to discuss the work that I had done at UNICEF on large-scale school mapping for universal school connectivity. All right, so just a bit of context. According to a 2020 report by UNICEF and ITU, approximately 2.2 billion children and young people, that's 2/3 of the world's youth, do not have access to the internet. And this lack of connectivity doesn't just limit children's ability to access online resources, but it also prevents them from developing the digital skills needed to compete in today's modern economy. And these disparities in school connectivity often exacerbate existing inequities and widen the gap in educational outcomes for children with and without internet access. This means that without sufficient access to the internet, children from the poorest households who are already falling behind will have very few opportunities to catch up to their peers. So in response to these challenges, UNICEF and ITU created what is called GIGA, which is a joint initiative, with a mission to connect every school in the world to the internet by 2030, and every young person to information, opportunity, and choice. And this is in line with our mission to advance as SDG 4, which is quality education for all children. Now, in order to achieve universal school connectivity, of course, you need to understand where each and every school is located. But as you can already imagine, unfortunately, complete and accurate school location data is scarce in many developing countries. Now, governments generally do have a comprehensive records of schools in their national registers, but these records often lack precise geographical coordinates, meaning the lat-long points. And this is especially true in many developing and least developed countries. So, for example, government partners in Senegal estimate that around 20% of schools are missing geolocations or lat-long points from their official data set. Meanwhile, in Kenya, 7,000 of the estimated only 7,000 of the estimated 33,000 schools have corresponding GPS coordinates. We also see instances where they have where the schools do have GPS coordinates in their data sets, but these geolocations are wildly inaccurate or erroneous. So for example, here we illustrate school location data from the Sudanese government, where you'll see that some of the points are located in the middle of the ocean or drifting across countries. So obviously it's incorrect, and without reliable and complete school location data, we do risk leaving behind the most vulnerable child populations. So again, at GIGA, we leveraged AI, specifically computer vision and high-resolution satellite images from Maxar to accelerate school mapping across the globe. So we started by first conflating and cleaning school location data across various data sources. And this includes, of course, official government records, but also publicly available data from OpenStreetMap and Overture Maps. And then for each of these points, we download the corresponding 300 by 300 meter satellite images with a resolution of 60 centimeter per pixel, centered on these locations. And we also did an additional cleaning step where we manually inspected each of these satellite images to ensure that the school is visible and distinguishable from the image. And what you end up with is a clean data set that we can now use for model development. So to train our school classification model, of course, we have the images of the schools, again, curated from government partners, OSM and Overture Maps, but then we also queried examples of non-school locations. These are our negative examples. So we queried OSM and Overture for non-school locations like hospitals, churches, hotels, community centers, residential areas, etc. And ultimately, we do find that schools do share similar characteristics that we can observe from overhead imagery, and these characteristics can be, for example, U-shaped, L-shaped, or O-shaped structures. They can be and especially in Africa, you have groups of rectangular buildings in a specific formation, and often you'll find that these schools have nearby playgrounds or open fields or sports fields. And then we train our simple image classification model to determine whether or not the satellite images contains a school. So as you'll see here, it's a very typical computer vision workflow using CNNs and vision transformer architectures. So in our experiments, we were able to show that we can achieve scores of 96%. This is in terms of area under the precision recall curve across 10 pilot GIGA partner countries in Africa. We also conducted generalizability experiments across the countries and within the African region. So here we show that countries typically generalize well to neighboring countries. For example, Benin and Ghana, Botswana and Namibia. And we also show that regional models do not provide significant improvement over local models, meaning local models tend to achieve strong performance and model performance alone. And this may be because schools within a country tend to look very similar to each other, at least visually from satellite images, but can be very different compared to other schools in other countries, meaning there's low variability within the country and higher variability across countries. So sorry, I think I'm missing one slide here, but one of the next steps after the model, training the model, model classification is essentially using class activation maps to pinpoint where within the image the school is located. So this is a model, essentially like a model interpretability approach. And we use this approach to sort of mitigate against the costly approach that is bounding box annotation. So here, basically, for each image where we identified, where the model identifies a school, we then ran class activation maps to further locate where within the image the school is located. All right. So here I demonstrate our example in Ghana. So to deploy the model, we start by downloading satellite images all across the country. So in this case, we downloaded around 1.2 million satellite images. These are over 300 by 300 meter or 500 by 500 pixel satellite images with a 50% overlap. And then to also save on storage costs, we only downloaded images where we found where we identified built up structures, and we used here GHSL to filter out images that did not have built up structures. And then for each of the images or each of the tiles, we then ran this through our AI model. The red tiles here indicate where the model has detected the presence of a school. And then again, we used model interpretability techniques to further localize the school location within the tiles. And as you can see here, our model was able to detect over 35,000 points, school points across the entire country of Ghana. And just to demonstrate some sample outputs here, this is one region in Ghana where the orange points here indicate government mapped schools, so schools that were identified in the official government records, and the blue points are points that were identified by our model. And you can see here, for example, this is a school that was identified by both our model and was already present in the government data set. but we were also able to identify additional locations, satellite image tiles that appeared to contain schools. And then when we cross-referenced it against publicly available records from Google, OpenStreetMap, and Mapbox, we were able to indeed confirm that these tiles do contain schools. But then you have some images here, for example, the one on the rightmost image, where we were not able to confirm using any auxiliary data source whether or not this is a school. And so for this, the GIGA team is also currently developing a human-in-the-loop model validation tool to help governments improve their school location data, where governments are deploying staff on the ground to locate and survey these schools. And this tool essentially is to help them identify previously unknown school locations and better allocate their resources for conducting these surveys. So before I end my presentation, I do want to highlight the meaningful change that comes with connecting schools. So you have here, for example, Nunkapir Primary School in Kenya. So GIGA helped to connect the school in June 2021. And since then, the school's academic performance has increased by almost 10%, with student population almost doubling in some grade levels. And I believe in the next few years, we are on track to connect even more schools and more students to the internet. And you can find the school location data sets are made available on GIGA's website, as you can see here. So that's maps.giga.global. All right, so just one last slide on what's next. So currently we are exploring the use of AI in Earth observation for climate resilient school infrastructure. So this is work that is being actively pursued by the global program for safer schools here at the World Bank. So it's essentially taking these two projects and merging them such that we are able to identify schools and then classify the schools based on overhead imagery and or aerial images and ground level or street level characteristics. So if you're interested in learning more about our work, we have our GitHub repositories publicly available, and we also have our papers accessible as well. So that ends my presentation. Thank you so much for your attention, and I'm happy to answer any questions.
Thank you, Isabel. I mean, this was fascinating. I personally related to it so much from our ongoing work, post-disaster reconnaissance work as well. So I guess independently from the type of hazard or disaster that you're looking into, I mean, the data scarcity is such a massive problem with so many different geographic contexts. So yeah, thank you very much for that. So there are two questions. One is coming from Iqbal Hussain. Iqbal, do you want to unmute yourself and ask the question? Yeah, lovely. Thank you. Or maybe he is not available now. I'll read it out loud. He's asking, I'm guessing this was done with high resolution, i.e. expensive satellite data. What are the options for doing this with open source satellite information?
Right, so that's a really great question. So unfortunately for the work that we had done at UNICEF, we used high resolution Maxar satellite images that was made available to us through the support of the US government. And this was global coverage. So that was what you would consider privileged information. Now, of course, this is definitely much more challenging to to acquire outside of that context. And so at the World Bank, for example, one way that we are collecting this information is by training staff on the ground to actually operate drones and collect this type of information on the ground by building local capacity. But to your question on doing this using open source satellite information, so I'm not sure if you're familiar with Open Aerial Maps, so I can link this in the description, but Open Aerial Maps provides openly accessible high resolution aerial images. So these are often like drone images, aerial orthophotos. So for example, one project that we're working on right now is St. Vincent and the Grenadines, and we actually found that Open Aerial Maps provides these high resolution Maxar satellite images. I believe it was 60 centimeter per pixel, openly available on their platform. They also have very high resolution drone images there as well. But note that this data set does not have global coverage. So this is often available usually in countries where there are like post-disaster sort of missions where the government sort of commissioned our consultants to collect this information and with their permission make it publicly available. So definitely that's an option. And then with regards to that's with regards to aerial images. I do want to also mention Street View images. These tend to be publicly available through Mapillary, and I think it's called CartaView. But then there's also the commercial counterpart, which is Google Street View images, of course. So
I see. Thank you, Isabel. It's very comprehensive. Thank you. So there is another question here. I have a million questions, but before going on to those, Kiyon Harpam, I think. Yes. Would you like to ask your question, or shall I read it?
No, I can ask it.
Lovely.
Can you hear me?
Yes, we can hear you.
Yeah, thank you for the presentations, both very interesting. I was wondering if the building data sets are available for use in hazard and environmental studies. We're doing a lot in the Caribbean at the moment to support development bank activities, and it would be very useful to have some of these data sets with more accurate buildings, their types, and all the attribution you mentioned. I am in the GitHub reference that you gave at the moment, and I can't find the outputs. I can find lots of code and some examples, which is great, but is the output data available, please?
yes, so
Kiyon, can you just, sorry to interrupt, Kiyon, can you just introduce yourself briefly so that we get to know each other?
Of course, yes. I'm Quillan Harpam. I'm a technical director at HR Wallingford in the UK, and I'm essentially a systems person, and we're at the moment doing a lot of projects to support the disasters and the disaster response activities in the Caribbean.
Thank you.
Right, so that's a great question. We do actually make our outputs publicly available. So I've linked in the chat, but I'm not sure if it's visible to the attendees.
I think it's just for hosts, but Rafa, maybe you can actually move it to everyone. Yes, thank you.
But maybe just to show you, we have so it's available through the World Bank Data Catalog, as you can see here, and you can actually download the GeoTIFF files, or rather it's a GeoPackage files and GeoJSON files, along with the corresponding documentation that describes how we generated these data sets. So all of this is publicly available through the World Bank Data Catalog.
Thank you.
Thank you, Isabel. And there is a question from Ricardo Herrera. I think it was on the same topic. The links that Isabel shared just now answer your question, Ricardo, or would you like to expand on it?
No, I think the questions were answered with that
Lovely.
reference to the data catalog.
Oh, but I do want to note, because these are the model outputs, with regards to the training data that we used as inputs to the model, unfortunately, the aerial orthophotos do belong to the government, and so in order for us to share that, we would have to ask permission from the government to share it with fellow researchers. So just
Yeah.
noting that here.
Yeah, I'm in Puerto Rico, so there's a lot of information that has been acquired over the years, especially after Maria. So I'm just curious about what other information is available.
And if you can introduce yourself, please.
Yes, I'm a structural engineer, retired, but I get involved in a whole bunch of building code related topics and so forth. So some of this GIS information is very valuable for things that we need to work with. For example, Florida has these requirements for milestone buildings. We need to do the same thing in Puerto Rico, but we don't have a data set of all the, multi-level buildings that would have to be included in those milestone inspections. So I'm trying to find somewhere where that information can be obtained, derived from, some of this aerial imaging.
Thank you. Thank you, Ricardo.
Thank you.
And the last question from our audience, Mohammed Adu Sidi Al Mokhtar, is asking how these data can be used to enhance climate resilience in vulnerable communities.
Great question. So,
If
while
Mohammed is here, maybe he could I don't know, expand on the question and introduce himself. Sorry, I just went ahead and read it, but sorry, Isabel.
no worries, go ahead.
I see that he unmuted himself, but we
Yes.
can't hear you.
Hello.
Hello,
Yes.
hi.
How are you?
We are good, thank you. Would you like to
Very
introduce
much for this
yourself?
good presentation.
Thank
My name
you.
is Mohammed Sidi Al Mokhtar.
Hmm.
I'm postdoc in UM6P in Morocco. So yeah, so I'm working on GIS, on climate change, and I'm working on Center of Urban System. So I want to know about this data, for example, AI and Earth observation data. If can be used, if this data can be used on analysis of vulnerability community. I don't know if I can understand. Yeah, this is my question. Yeah, thank you very much.
Thank you, Mohammed.
Got it. Yeah, thank you so much, Mohammed, for the question. So while vulnerability analysis was beyond the scope of the work that we had done, it was really mainly focusing on generating exposure data sets. These AI-derived structural building data sets are intended to be used as decision support for, say, aggregated statistical analysis and spatial prioritization. So for example, the work that we're doing at Disaster FCV team, Disaster Fragility, Conflict, and Violence Nexus team here at the World Bank involves overlaying exposure data sets and hazard data sets and generating aggregated spatial statistics. With that said, I do want to emphasize or note some of the limitations of these data sets. So one is that it's not a substitute for ground surveys, especially in high stakes decisions concerning like structural safety or regulatory compliance. So this is because of the limitations of these data sets, limitations such as the invisibility of critical structural attributes, attributes like roof to wall connections, internal structural integrity, and these all limit the model's reliability for more detailed vulnerability assessment. So I do want to emphasize that. And so I would say that these AI-derived data sets are really not meant for decision-making on an individual building level, especially without further field verification. And I would say it's best suited for neighborhood level statistics and supporting the planning of targeted field work. So I just want everyone to be cautious and understanding of the current technical limitations of this work.
Thank you, Isabel. I would like to follow up on this actually. So in my mind, listening to your presentation, the data sets to me looked very promising in an event of a crisis, because, for example, we have seen this, time and again, after major problems where lots of schools are impacted and they have to shut, and you actually have to allocate the students elsewhere to ensure that the education is uninterrupted. So I was wondering if you envisaged a use like this for your data sets, or has it been put in test and use in an event of crisis like this, or else, in the geographic coverage for which you have developed this data?
Right, that's a good question. Right now, not so much. It's at least for the school location data set, the main purpose of that is really to identify schools for the purpose of connecting them to the internet. But I do know that UNICEF GIGA is also expanding their work to also cover instances such as what you described, which is looking into applications for climate resilience and disaster response as well. So I think that's something that we can look forward to in their work.
Thank you, Isabel. Thank you. Afsana has her hand up.
Yeah, this is very interesting, and it's exactly what we want to see, the kind of application. So you mentioned that you manually scanned through like 300 by 300 images of the entire country scale at some point, or was it? I didn't understand it very well, and I just was wondering the size of team and the kind of operations that you were running, like the time scale, how much time and effort this required is a question, and also the processes that you have developed. Would you suggest that this can be used given any input data, not specific to the geographic locations, but for other locations where we are able to somehow generate these images or obtain these satellite images?
Right, that's a really good question, and I definitely agree. Like one of the main bottlenecks in the model development workflow was generating clean data that can be used for model training, and I would say this was probably what took the longest time. I would say for a small country, it could take a few days to go through the images. So in this case, we would scan through let's say 5,000 images of schools, 5,000 images where the government says there are schools, and filter out the ones where it's like in an open field or where it's in an uninhabited area. Of course, this data set has already been filtered even beforehand using auxiliary built up data sets like Global Human Settlements Layer, believe it was WorldPop, and the World Settlement Footprints data set. So we use a combination of these different built up data sets to figure out where there are infrastructure, whether or not there are infrastructure in these satellite image tiles. And if there are no infrastructure, then we just disregard them. So there's already sort of a filtering process. But I think there could still be some work done in terms of even like speeding up this process of manual data cleaning even further. So one approach that we had tried, for example, was looking at the visual similarities between schools across countries. So for example, if we had already trained the model in Mongolia, and we find that the schools in Mongolia are very similar to the ones in, say, Tajikistan, then what we would do is we would run the model trained in Mongolia and Tajikistan, and have sort of these initial pseudo labels of schools and non-schools. And we would run this on the schools data set from the government. And so if we find that the model trained in Mongolia, if it says that a school that was labeled, a satellite images that was labeled as a school in Tajikistan to be not a school, then we only look at those images. So it's a way to speed it up a little bit more, but I think there could be more advanced techniques to further improve this. So yeah, so it's definitely I would say like a work in progress from Giga side.
Okay, thank you. Thank you, Eva.
Thank you, Isabel. Again, if I may, with a follow-up question, so the bit in your work where you have differentiated the school buildings from the other public buildings was of much interest to me, because I guess the methods and the approaches that you have developed could be, of course, you know, important for other critical infrastructure, for example, healthcare facilities. And you have explained why your model worked well in differentiating schools from the other non-school public buildings was because of the shape of the schools. So it can be a little bit out of scope, you know, of your work, but I wondered to myself if the model was equally successful in picking, for example, healthcare of all the public buildings, and how do you think it would perform if we compare the hospital or healthcare facility recognition across countries, for example? Do you have any insights or any idea how it would perform?
Right. So that's a really good question. And I do know that UNICEF Giga is specifically interested in expanding our work to healthcare facilities. With that said, I think the biggest the biggest thing that could determine whether or not the model would be successful is whether the buildings, whether healthcare facilities are distinguishable from satellite images. So one sort of approach that I use is to just look through the images, and if I myself as a human can differentiate healthcare facilities from other types of infrastructure, then you would expect a machine learning model would be able to do so much faster and scalable approach. Of course, if it's not possible, especially for smaller healthcare facilities that look a lot like, say, residential or other types of non-residential images, then that's an inherent sort of limitation of the models. But I did sort of try to look into this before I think it was one country, not sure if it was South Sudan, but we did see that for healthcare facilities, they do tend to follow a specific type of structure. Like they tend to be like H-shaped structures. So I guess I would say it would depend on the country, like whether or not their healthcare facilities or hospitals follow a certain type of structure that can be distinguishable from satellite images. And to your question of whether these models are generalizable, again, it depends on the country. Like in some countries, even schools, like for example in Brazil, we found that the schools were very hard to determine, and we were very hard to differentiate from other non-school infrastructure because they just look very similar. Yeah, and you also have to think about like how schools look like in urban areas versus rural areas and how they differentiate, how they differ. So yeah, so a lot of things to think about.
Indeed. Thank you, Isabel. Now, going back to questions from our audience, first of all, Ricardo is asking if you can share your contact email. I don't know if it was, at the last slide, Isabel, contact information. Maybe our audience might not have been able to jot it down. So if you would like to share it. And another question from Ricardo is, for large hospitals, evidence of emergency rooms, ambulance canopies might be clues, he says. I guess it's just a comment if you'd like to say anything on it. Okay.
Yeah.
I would like to invite Ashish Timilsina to unmute themselves and present themselves and ask their questions if they are here. Thank you.
Good afternoon, ma'am. It's me, Ashish. So I want to know, since I come from Nepal, which is a country with varying altitude approximately from 60 meters to summit of Mount Everest, that is 8,848 meters. So in these countries and other similar countries, how can we ensure that these AI models which you discussed here remain accurate as they have different architecture styles and materials? And my next question is like, since I am from engineering background, so this attitude influences both building vulnerability and water contamination. And how might the AI-driven Earth observation workflows be adapted to assess the structural resilience and environmental risks across these diverse terrains?
Right. So you mentioned diverse architectural styles and materials. So in our work, what we found was that we tried to train our models on a country-specific basis to make sure that the models are locally relevant and align with sort of the building taxonomy within that country. So what I would recommend is working with for AI experts to work and technical experts to work with engineers such as yourself to figure out what are the different building taxonomies that are relevant in your specific context and develop the models around that. And I think that is the current approach that's being done, for example, by the Global Program for Safer Schools, and even in the work that we have. As we found that.
Thank you, Isabel. We have another question from Jingje Wu.
Yes, hi. Thank you, Isabella, for the fascinating presentation, and good to see you again through this webinar. So my question was that for the school mapping that you did you observe any potential like bias, inequality in the model picking up bigger schools that have more pronounced features, like if they have playground or have complex shapes, so it's easier to identify comparing to those small rural schools that may not be easily differentiated from other either residential buildings or other public buildings? And if you've seen that, how would you recommend mitigating this type of potential inequality if we use your results data? Thank you.
Ginger, would you introduce yourself, please?
Oh yes, sorry. So yeah, I'm Ginger. I'm a disaster risk management consultant from the Global Program for Safer Schools. So, as Isabella presented, hopefully we will be working together soon. So yeah, thank you. That's my question.
Thank you so much, Ginger. So to your question, I actually have like a backup slide here that shows you the work that we had done on so what we had done at UNICEF was we stratified the data splits such that we have an equal representation of rural and or we have a representative sample of rural and urban schools within each training, validation, and test data split. And what we found was that our models actually perform better in rural areas, as you can see here, like marginally better in rural areas compared to urban areas. And this was because schools, and this is very specific to the African region, schools in rural areas in Africa, they're very pronounced in the sense that you can see that these schools are often long rectangular buildings, as you can see here, surrounded by an open field. And once you see it, you can automatically really say like this does indeed look like a school, at least in the rural context, because the surrounding non-school or residential buildings in rural areas tend to be these very small buildings that are close together, as opposed to this one huge structure that as you can see here, surrounded by an open field. Is very indicative of it being a school. Now, in urban areas, you'll have schools, as you can see here, but they also tend to be very similar to other non-school infrastructure, like police departments, hospitals, community centers. So that's why it's actually a little bit harder, or at least we surmise that it's a little bit harder to identify schools in urban areas, just because of how similar they are to other non-school infrastructure. So that was an interesting findings from our studies. So yeah, I think just being cognizant of the disparities in or the difference in model performance across different types of regions, rural or urban, or basically stratifying your data when you're doing model testing, I think is important to bring to light potential model biases and yeah, and other issues.
Thank you, Isabella. My question is mainly from our some field experience that we have in countries that's not in Africa, that we've observed that could be potential challenges in differentiate schools in rural areas. But yeah, hopefully with your help in the future, our programs can helping this type of school mapping in also other countries. Thank you.
Thank you. Okay, so we have one request that's been voiced by Ricardo again, but it is something that everyone on the school will benefit from. Is please references to the papers and resources that you have shown at the end. Maybe we can organize that, Rafa. I don't know how we should do that. Maybe in the form of an email if it's too difficult to put on a chat now. But yeah, thank you so much. I don't know if there are any last words from our team. Yes, Dina?
Yes, if I may, no, I was very interested in the work on the Caribbean island, and I was particularly, we have done some work in Dominica with PhD student Sara Espe, which I think she's also on the call, and we were wondering whether you had attempted to recognize damage with your assessment of both the roof and the vertical condition of the structures for Dominica?
Right. So as of the moment, it's mainly classifying rooftops based on the roof material. So in terms of damage, we might be able to use like blue tarpaulins and incomplete as proxies, but I think there could be further research work done to actually hone in on damaged structures and further quantify on a more granular level the level of damage for each of these buildings. So I think that's that would be a very interesting like future work, and something that I would also hope to work on maybe in the future.
Yes, then maybe, yes, it would be interesting to collaborate on that. And I was just wondering, the picture that, the images that you used for that reconnaissance system were actually maps from 2017, and so from the time of the event itself.
Yeah, so that's actually a very important point, because the models that we developed were trained on post-disaster context, and so it's so the model was trained to be able to detect blue tarpaulins, incomplete buildings, which were very prevalent in post-disaster, post-Hurricane Maria, Dominica.
Yes.
But we actually ran some generalizability experiments, and we found that models trained in post-disaster contexts in Dominica did not perform well when you run it for not like say pre-disaster or non-disaster contexts in St. Lucia. So I think that's a very important thing to consider, is that your
Mhm.
models are highly contextualized to the local region and to the context as well.
Yes, to the event, because
The
I
event,
think
yes.
the construction type of St. Lucia and Dominica are not too different. So in theory, especially as far as roof types are concerned. So yes, interesting that it doesn't quite work as well.
Yes, because the distribution, right? Like there were so many more
Yes.
blue tarpaulins in the post-disaster Dominica than there were no
Yeah.
blue tarpaulins in St. Lucia. So I think it's very interesting.
And have you done any studies with subsequent imagery, so to show to see whether the model is able to pick up recovery, for instance? At some point, the roof will be rebuilt and hopefully the tarpaulin will disappear, which means that if you use updated imagery, then you will be able to trace the recovery process.
That's very interesting. So as of the moment, not yet, but I think that's something that the team would be very interested in terms of monitoring sort of the resilience and recovery of these countries, at least in the housing sector.
Yeah. Thank you. Thank you. But anyway, fascinating work. Thank you.
Agreed.
Thank you so much.
Thank you so much, Isabel, for accepting our offer and, for the amazing talk and answering all the questions. On behalf of the team, it's been wonderful. And thank you, everyone who attended as well. You're gonna have access to the recording of the session on our website in due course. Thank you.
And thank you, Ricardo, for sharing some other resources, which I think the rest of the colleagues can see online, and it can add to our community knowledge. Thank you very much.
Indeed. Have a good evening. Bye.
Thank you so much.
Bye-bye.
Bye-bye. Thank you.